Morning everyone and welcome to the Machine Learning Coffee Seminar. Before I give the floor to today's speaker, I remind you that you are welcome to ask questions already during the presentations, and when you want to do that, please just raise the hand button that you can find from the participant list on the bottom. So use that one and then I'll give the floor to you. But today our speaker is Professor Jussi Kangasharju from the Department of Computer Science, University of Helsinki, and he will be talking with the title of Intelligent Container Overlays. Please go ahead, Jussi.
Okay, so everybody, good morning. Here, let me start the presentation. Okay, so the topic of today, as Laura said, is intelligent container overlay. So this is more of a networking topic, as I'm working in networking, but there are, as you might guess from the link word intelligent, there are also links to machine learning, and I will sort of first present the concepts that we've developed, some of the results we've gotten, and then sort of end with kind of ideas for possible links towards machine learning and areas like that. And most of this work was presented at the ACM Hotnets workshop in 2018, which is kind of the leading venue for presenting new networking concepts. And some of this is still work in progress. So the lead author is Alex from my group here at University of Helsinki, plus we've had a couple of other collaborators from different parts of the world as well. Now, what's the motivation? Edge computing was one of our key motivating factors. So here, if you have a popular application today, these may be deployed to these various, from the cloud towards edge devices to help to shorten the latencies, to improve the quality of service for the users. And things seem to be working fine most of the time. But then we kind of ran into the issue that what if suddenly the app or service becomes very popular in a very different part of the world? So how would these people then be able to access these services? So if they access the service from its original location, this is of course a bit slower. Users might not be happy. So it would be nice if we could somehow migrate the services closer to the users. And so there are multiple questions there. So today I'm going to be talking more about how to migrate it, but there are also questions related to how to discover the local services. Are there any? And sort of building all of this together. Now, if you're familiar with the way internet has been designed, internet services are deployed. So you've probably heard of content delivery networks, networks like Akamai or Cloudflare or things like that, which today deliver pretty much all of the services on the internet. And this development has been going on for the past 20 or so years. And all these extensive scalable deployments are the reason why the internet has not really suffered at all from this current corona situation. So basically it's been business as usual for the internet. But this is not what we are after. So this current infrastructure works fine, yes. However, it is very much a siloed infrastructure. If you're a customer of one provider, Akamai or Cloudflare, then you are stuck with their services. What we are after here as sort of a bigger picture vision is to have a more of an open standard for deploying these services on the internet, a decentralized solution without these central entities managing and controlling everything. So in essence, very much something like the current internet, an open standard for service deployment on the internet with open service migration, everything being decentralized. And as I said, some of the motivations that we've had come from this edge computing, which is now starting to deploy all these possible compute servers all over the very close to the users, making these edge deployments pervasive. And we believe that the applications that you deploy on the internet, applications and services, they should autonomously unfold towards the edge so that you don't have to manually manage and select locations where to deploy various services. And the only management that you as a service provider or service operator would have to do is setting high-level objectives, like how quickly should the service react, how much money can it spend, what's the budget, and so on. And at the same time, we would like all these services to autonomously adapt to changes in their environments. So in short, what we are working towards are common standards for self-organized service provisioning on global scale. So when you put it that way, it's not just about the edge. So of course, this can be applied to cloud computing, any kind of service provisioning on the internet. This edge computing is simply a nice vehicle for showing the need for this, as the number of edge providers may be very high. So manual centralized coordination may not be very easy. And the concept that we've developed is the ICON, which stands for Intelligent Container. And what it is, you may have heard of containers, which are today used in many different environments for encapsulating services. But for us, the word container here is just a catchy term to represent any kind of a virtualized entity that can contain a service. It can be a technical container like a Docker container. It could be a virtual machine, could be a unikernel, could be any kind of a virtualized entity that can be moved to run in a different place. The only reason why we pick the word container is because then with the words intelligent container, you get a nice acronym like ICON. So that's the reason why we call them containers. They don't technically need to be them, although as an implementation, they are a pretty good way of doing it. And this kind of a container view towards applications brings up this kind of a microservice architecture, where an application is actually a collection of services that are either more or less loosely coupled to each other. And the two key things that we require from these containers, which are kind of something that a normal container, which is just a place for running code, is not able to do. So we need some additional code around it. So the first capability we need is the capability of these icons to observe their environment. In this case, meaning monitoring where the incoming request flows come from and discovering potential deployment locations. And the other capability we require from them is that they are able to take decisions and act on those decisions autonomously. And the actions that we foresee, there's three of them. One is for the icon to migrate to a different location. One is that it replicates itself to a different location, so then the original one continues to run. So the reason here is that usually you would want to migrate or replicate because there's a large number of users coming from some new direction in the network, and in order to satisfy your latency objectives, you want to serve them from a location that is closer to them. Or the third action that an icon can take is to terminate in case it discovers that it's no longer needed at its current location. So on a high level, so this is what the world looks like. So here we have the icon running. Originally, let's say it runs on some cloud provider somewhere, and the application owner only sets high-level goals, such as what should be the latency that the clients experience and how much money is the icon allowed to spend. So basic, of course, running a service anywhere on any kind of a deployment location is going to cost money. So that's why it's important that the icons have a budget. Otherwise, if you have no budget constraints, then you just deploy an icon everywhere and you get the best possible latency. So the icon here monitors the incoming flows. Where are the requests coming from? And then based on that, it makes a decision, looks at, are there possible locations to deploy? So let's say here in the bottom right corner, you have more users coming, more requests coming from there. Icon initiates discovery of possible deployment locations, discovers this place there and then replicates itself in that location. And then the users in the bottom right corner near that location, they will start using the replica of the icon that is nearby, and therefore they get a better service. And for the application owner, now the cost is having to run 2 of these instances, but of course the overall request load has remained the same. Or in some cases, like here showing example on the bottom left part of the figure, the icon that was running on one location might decide to migrate closer to the end users if a larger number of users appears from one corner in the network there. So as a sort of more global picture, if we look at it, so there is some origin, the icons, the origin can replicate itself into multiple locations, and each one of those icons is able to autonomously then further replicate itself or migrate towards other locations. So basically you have this, although there is the origin point, but each of the icons that is running is also able to perform actions autonomously and does not necessarily need to contact the origin. Of course, there is one feature that we kind of, the life cycle of an icon, it gets created somewhere, then it runs and operates. And if it runs out of money, what we have also designed is that it can actually call home, call back to its parent or the origin to ask for more money. And so that is also, of course, then it's up to the application owner to decide how to allocate the resources. Now the network as such, especially when we start looking at it from a single point of deployment and from going from there towards all the different clients. So the internet, of course, it's not a tree. It's very much of a different kind of entity. But if you look at it from one point of origin towards a set of clients, it's very much a tree-like topology that you get. And as our first attempt, or the first concepts that we defined, we decided that, okay, let's look at a tree that is rooted at the origin. So this is the cloud point where the application is originally deployed. And from there, it starts to observe where are the requests coming from and where to deploy replicas or where to migrate. And the reason why we picked a tree is because, as I said, the real topology from the cloud to the clients, it's very much tree-like. So there may be some parallel links, but it's very rare that you would have a much more complicated structure. And also the tree makes it much more efficient to control, to propagate information and so on. And the key things here are, there is the coordination and control. So the blue arrows here, they show links, information that the different icons are sending back to the origin. So in this case, the critical points would be how many requests are coming, how many users are served by me, and what are the latencies that I am seeing towards those clients. And then as this information flows upwards, different icons along the path can take different decisions about where to deploy or where to migrate. The red arrows going down, they are then more the control flow. So in case the origin wants to send messages or control the lower icons, that's also possible. And these greenish dashed lines here, they are sort of this last point that I have on the left side, that maybe we could use some other topologies, more swarm-like. So to have these icons not be in a strict tree, but to have a much more fluid or different kind of a more flexible topology. This is something that we are still kind of working on and trying to figure out whether it makes sense or not. And one concept which is something that does not exist on the internet yet, which is sort of fundamental to these icons, are these what we call independent edge providers, or IEPs. And these are the facilities where the icons can deploy themselves. Now, I just said that these don't exist. This is strictly speaking not true, because these could be any facilities operated by any cloud providers, like CloudFront operated by Amazon or Azure Stack. All these big cloud providers have started to deploy what they call these edge solutions. So these could be IEPs. If you talk about edge computing, you will run into this concept MEC that's proposed by the telecom operators. It used to stand for mobile edge computing. Nowadays, it stands for multi-access edge computing, but with the same acronym. So this is the ideas of the big telcos to deploy edge servers or edge clouds in their own networks close to the base stations. Or possibly, since we take the open spirit of the internet, why couldn't these IEPs also be crowdsourced? There are already a bunch of platforms that offer these crowdsourcing computation. You might be familiar with the BOINC project from Berkeley with SETI at home, Folding at home, all these things. These are examples of that. And we have these more general platforms like iExec, Golem, and so on that already exist. So these IEPs, even though to a large extent they sort of don't exist, but at the same time we see that they partly exist, and we see that, you know, an enabling and market for these would be a useful thing, because it would make the service provisioning also more democratic on the internet. But the thing that we require from these IEPs is that they run this, what we call the container yard application, which can be built on top of any of these existing container frameworks, Kubernetes, Mesos, Docker Swarm. And this is the software that negotiates with the icons, or coordinates with the icons about when does an icon want to deploy at a given location, what hardware resources does it need, what's the price, and all these. So there needs to be some additional software that handles the coordination on top of this standard Kubernetes or other container platform. And obviously, this brings up the issue of contracts, agreements, transactions. So if the icon needs to agree with the IEP about how much does it cost to run there, we need some way of enforcing that contract. And smart contracts is one option that we've looked at. They sort of work for some cases. Of course, the more distributed you go, the harder it is to come up with solutions. And so this is very much an open problem still. But fundamentally, so we have done our work with the assumption that anybody would be able to establish an IEP. Of course, it may turn out, if these things become a reality, that in practice only a small number of players like big cloud providers, big telcos establish them, but we want to develop solutions where anybody could establish those, hence the importance of these open and standard solutions. A few words about the discovery of these IEPs. So this gets a little bit technical on the networking side, but just goes to show more that all the building blocks are there. So in order for all of these IEPs to come into existence, you don't really need anything except to set one up. And we assume that the IEPs want to get containers or icons running on their services. So we assume that they're willing to do a little bit of extra work by adding information into the domain name system, basically the directory of the internet, about which services they are able to host. The clients are able to, they know the addresses of the clients. They're able to do trace routes, so tracing, building a map of the network from the icon towards the clients. And from those paths, you can identify which are the domains that are on the path to the clients. And then from DNS, since the IEPs have entered the information into DNS about what are their IEP locations, we can identify those, and then the icon knows that if I want to deploy myself closer to these users in this user group 2, I have the possibilities of this one server in domain A and the other server in domain B. And then it knows where it can deploy. Then it can figure out how much does it cost to deploy at domain A, what are the latency implications there, how much does it cost to deploy at domain B, what are the latency implications, and so on. Now, of course, here, if you think about this picture, the icon at the top, it sees the combined requests of user groups 1 and 2. And if it deploys itself into domain B, then obviously it's not able to serve, if it replicates there, it's not able to serve any of the users in user group 1. So a more cautious decision might be to replicate just one stop, one hop, and then see how the situation evolves. But this, of course, is part of the decision-making process of the icons. That's kind of the part where we are looking for additional collaborators. Now, the intelligence of these icons, the simple version that we have so far implemented and evaluated is basically a utility function where you have two elements. You have the budget or the cost, and you have the latency, and then you have some weight between them to tune this. And basically the decisions are then done via thresholds. So when the expected utility of an action is higher than or lower than some value, then you either replicate, you migrate, or you terminate. Or a more complex version is that this could be that the overlay, the icons themselves coordinate and form a picture of the world and then adapt the network as a whole instead of these individual icons. Now, a few words about this. This is now the work in progress part about this decision making. So we have this simple utility function where you have the latency as one input and the cost of running the icon at a location as the other one. And here we look at the icon looks at a subtree rooted at its current location, and it identifies all the possible IEPs in the subtree. And then by starting from the bottom the leaves and working its way up, it looks at where did the request come from, what would be the latencies, what are the costs. It calculates the utilities for the next time slot, and then you deploy the icons according to that. And then in the next time slot, you again do the same math and so on. And using time slots is most of the times pretty, it's not a big issue because the requests generally do not change that rapidly. So you might have, running time slots of 10 minutes or so is in most cases perfectly fine for adapting the traffic load. So it's very rare that the traffic loads would shift that drastically in extremely short time scales. Now, we did some preliminary performance evaluation. We compared our simple algorithm, which we have in a paper draft, which with 3 other algorithms. So one is the cloud, where we deploy everything just in the cloud, don't do any icons. One is where you deploy an icon everywhere. And then we have this Oracle approach where which knows that what would be the optimal deployment for the next time slot, and it follows that. And as the request traces, we use trace from the World Cup '98 data from their server. Now you might ask, is a 20-year-old data set still relevant? It's a valid question, but there really isn't that much fresher. There are not that many good request traces available. So this was the easiest we could find, which has the nice property that is distributed geographically. We can cluster the requests. And we use, as a network topology, we use the network topology from CAIDA, this Center of Internet Research in UCSD in San Diego. Their topology of the US West, so western part of the US, and we put the origin cloud at an Amazon location also in US West. And for the prices, we took Amazon's spot pricing just to get some price variation. Otherwise, if all the prices are always fixed, then it gets very boring. And here, if we look at the latency, so the green one is where you deploy an icon everywhere. So this is where you get the lowest possible latency because all the possible locations are covered. The red one at the top is when you deploy only in the cloud. And then you have the blue and the orange lines. So the blue is the Oracle, the orange is our icons. So you can see that while we are not quite as good as the deploy everywhere, we are pretty close to the Oracle approach, and obviously significantly better than just deploying in the cloud. Now, if we look at the distribution of the latencies, so here the x-axis is logarithmic in scale, just to see the smaller values a little bit better. You can see that for any of the a bit higher values, we are just as good as the deploy everywhere. And for the smaller values, the difference is not that huge. It looks acceptable. And of course, then if you plot the cost as a relative cost, so icons are able to get this performance, which is very close to the deploy everywhere with only half of the cost. So this is a pretty reasonable starting point. And even the Oracle approach isn't going to be able to get much lower cost than what we were deploying. So this sort of looks like a very promising first step. And of course, there's a lot to be tuned here, but even this kind of a simple solution, simple utility-based solution seems to be doing reasonably well. Sorry. So some open questions that we have now. Of course, the big one is that, so how much of intelligence do the icons actually need? So if a simple utility-based function is able to get a decent performance, is it worth it to make it something more complex? We don't know. So then a technical question, which is more of a networking problem, is that how do the clients discover their closest icons? So this is sounds simple, but it's actually not that simple. Of course, security questions come up. If you assume that these IEPs can be deployed by anybody, well, how do you trust all those people to run your code? In the current cloud environments, it's very easy. You have a small number of big providers, you make contracts with them. If they violate those contracts, you can sue them. But you have random people running IEPs, how do you sue them? And then the agreements, not just the security part, but just agreeing that, you know, between the icons and the IEPs, was everything provided as was requested? Are the smart contracts a good option? How would we need to handle this? Again, keeping in mind that ideally we want to follow a decentralized solution. Now, future work on the icons. So what we are now working on is we're implementing this container yard. This is already ongoing work. Something where we're thinking about is how do these icons negotiate with the container yard. So again, here you need some kind of a standardized negotiation protocol, like same way as all the routers in the internet support IP, all these IEPs, any kind of a service deployment location would need to support this service negotiation protocol. This intelligence, possibly one addition there could be some prediction about where the requests will come, because all these migration replications, they take a bit of time, so it's not instantaneous. Starting a new virtual machine at a big cloud provider easily takes 5 to 10 minutes before it's fully up and running. So you might want to, some cases, try to anticipate and predict where the requests are coming from. And then, of course, the interesting question that we have not touched yet is that if all the world moves into deploying all the services and applications using icons, then we end up in a situation where the icons are competing icons for different services are competing for the same resources. So what happens here? And then, of course, this chaining of icons, how do we manage that, and so on. So this is another coordination type of effort. So just in short summary, so why do we think icons are good? We think that the IEPs are a good way to tackle these growing demands, not just edge computing, but service deployment in general. It reduces the monopoly of the big cloud providers. And this kind of an open infrastructure enables anybody to start deploying services on a global scale. Administrative overhead is lower. Everything moves by itself in the network, where you just set the high-level goals, high-level targets. And icons being able to make autonomous decisions then makes everything faster. They're able to adapt better and quicker than humans would be. And now this links to this machine learning adaptation. So this first point, as I already mentioned, is this intelligence for the icons. So the question about how complex would it need to be, and would these non-tree solutions make sense, or is it enough to basically the question being that, is it enough to work with the simple utility functions in a tree-like topology? Then a more general topic about adaptation and so on is in general learning in the whole network stack. So I have a project with Aris Gionis in the Academy's IEPS program, where we are doing exactly seeing how to do adaptation, intelligence, learning in the network. And one, for example, concrete point there could be these multipath communications. You may not have heard those, but if you use Siri on your iPhone, you have actually used this multipath communication. So there's this multipath TCP protocol that has been specified, has been deployed. And there, of course, the interesting questions are that how would you schedule your traffic across the different paths that you have available? So this is one area where people have thought about using machine learning or adaptation. And then there is a big concept that is coming up, is called Edge AI, topics also like federated learning, autonomous vehicles, drones, and so on. And so these, of course, are areas where it may be interesting to look into something together. But that's it. Thank you for your attention. And if you have any questions, I think Laura will handle the practicalities.
Yes, thank you, Jussi. So definitely, do we have questions from the audience? So please remember to use the raised hand so I can see that you're asking. So, well, while the others are still thinking, I can start with my question. So you said that you still anticipate that the IEPs will be established by the big players. So how much do you think that it will then release the monopoly, and what do you think will be the reason for that? So is it a cost question, or just difficult to get into the business there, or?
So while I said, I mean, yes, we assume that the big players will also deploy those IEPs because they have the facilities already. The way it will reduce the monopoly is that it opens also the door for all these telcos. For example, one of the reasons telcos are so eager to push 5G is because it has these edge clouds and these kinds of processing closer to the edge, which is the domain of the telcos. So they kind of are pushing that because it means that they get some of the data away from the big cloud providers and they get to do something useful. So while it's not clear if we are able, running into this kind of a scenario where you would have, every possible little provider providing their own edge services, that I don't know. There is some companies called Vapor.io in the US that's already selling a service, or at least planning to sell a service, where they deploy these boxes at the base stations and then basically like IEPs, and then you can rent space there to run your services. So while it's going to start off, I think, with the big players, but if you have an open set of solutions, then anybody could join. So of course, we'll see in the future how this will actually turn out.
Okay, great. Yeah. So thank you. So do we have other questions from the audience?
I'm not able to raise hand because I seem to be a
Yeah, you're
host as
host.
well.
Yeah.
So I'll just ask. So I have a naive question about, so some of the computation, of course, will be still done centrally in the cloud. So
Yes.
how does this work? So is it all of these edge deployed solutions can of course communicate, and they need to then optimize themselves how much of the computation they do in the cloud and how much in the deployed location. Does this produce some interesting intelligent decision making needs, or is there some straightforward way of solving this issue?
Yeah, that's a good question, and that's definitely a relevant problem. So the one comment that you can say about these icons is that if everything needs to be encapsulated into a single service, it cannot be very large, or it cannot work with a large database if it needs to migrate. So you obviously need to coordinate with the cloud. So the one big question is that if you have a service that's running on a big database, where is the database? And if you need to do any bigger operations, so at the moment, the most sensible solution seems to be that parts of those services are running on the edge in these IEPs, parts are running in the cloud. And as you said, then it's an interesting question of how to split the application. And there we don't have anything concrete yet. So that would definitely be an interesting topic as well.
If there are no other questions, could you elaborate on your thinking on the federated learning? Because that's, of course, very obvious that people want to keep their data with themselves on some applications, and then you will want to bring the computation where the data is.
Yes. So, I mean, definitely this is sort of, we've been on a different work that we've been doing. We've been looking at these sort of technical reasons for deploying edge. And sort of from a performance point of view, most of that stuff does not seem to make sense. So the cloud is actually already close enough to for most applications, the cloud is already close enough. But then you run into this question, like you said, is that people want to keep their data with themselves. And I think, I mean, this federated learning approach, we haven't looked into them in deep detail, but I think these are especially interesting and useful. The one challenge that I see in this, when you're pushing stuff towards the edge, is that how much processing capability do you have at the edge? Because that will limit the ability of what you can do. Or well, not the ability, but at what speed can you do things. So we did, for example, a test where we were doing object recognition from video, and we were doing it with a regular laptop here so sending from a mobile phone to a laptop here in Helsinki, doing the processing there, or sending it over the network to Hong Kong to be processed with a GPU. And overall, you get results faster with the GPU in Hong Kong than you get from a local, regular computer here in Helsinki.
Cool.
So, so that's I mean, for all this federated learning and these kinds of approaches, if you need a lot of computational power and you need it fast, it's going to be very expensive to deploy an edge that's able to handle that. And that's sort of but then there is the aspect that sometimes you don't want to keep your data, you're willing to wait. Not everything needs to be done in a split second. So as an environment, I see this as an interesting environment to see, because there's been a lot of hype around this edge and all of that stuff. And the more we look at it, the more there seems to be hype. But I think there are also some interesting areas where it does make sense. And the interesting areas are, I don't think they're not related to performance, but they're related to these other properties, like wanting to keep your data to yourself, these privacy types of aspects and so on, or keeping data local because it's only of local interest and so on.
Yeah, thanks. A really nice answer.
Yeah. So do we still have questions from the audience? Well, it seems not, but then thank you very much, Jussi, and I'm hoping to see you all again next week in our machine learning coffee seminar. So have a good day. Bye bye.
Thank you.